warahmatullah. My name is Kushal Mohammad Haider. My ID is 200212009. Today we will explain the topic is rectangular waveguide. Previously we discussed about parallel plate waveguide. Here things are pretty similar, but the main key difference is here we deal with total 4 surfaces. In the case of parallel plate we deal with generally two surfaces, this one and this one, but in the case of this topic we will deal with this surface and this surface also, and thus this will increase our boundary conditions and that stuffs, but rather the equations will be same. Here we see a rectangular conductor which weight is too much larger than his height, we can see, and the total surfaces are this surface, this surface, this surface, and this surface. Total 4 surfaces is purely conductive body. Here then, in today we will derive two equations. One is for transverse magnetic and one is for our transfer electric. Here we will take some help from a video also in this case. For firstly we see the transverse magnetic wave. It's our Helmholtz equation we studied earlier. For transverse magnetic we know our Az component will be 0. Then if we see, then we will go for our boundary conditions. I said earlier, we will deal with 4 surfaces, and for y goes to 0 in this surface we can see Ex and Ez will be our 0, and y goes to b in this surface the condition will be same, and for x is equals to 0 and x is equals to a, we can see our Ey and Ez surface will be 0. This is our boundary conditions, and then if we will derive the equation for our Helmholtz, some mathematic manipulation, we will get this result. This is our main result. Here we can see our main result. Here we can see our main results. Then by putting these boundary conditions, by putting our result, mainly we can get the cutoff frequency. Kc is equals to kc square is equals to k cutoff frequency number mainly actually, and the previously we derive some value and we get the equation of this equation, mainly this equation. Then it's time to put our boundary conditions. We put our boundary conditions here and here. By putting our boundary conditions, mainly we get these two equations. One is kx and one is ky. Kx is m pi by a and ky is n pi by b. Here m and n is 1 2 3 4 and furthermore any rational number. In this case, here we can see there is a word Ez vanishes for m is equals to 0, n is equals to 0. Here the main portion we can get, wait please. From this one, in the case of Ez, if we see Ez, we will see Ex, Ey and these components Hx and Hy, it will be 0 our components. Okay, then if we put the value of kx and ky, m pi by a and pi a, we will get our cutoff frequency. In this case, cutoff frequency we will get here. We can see a important line. If m or n all is equals to 0, ez will be 0, which means all fields components are 0. So tm00, tm01 and tm10 are called non-propagating mode. So minimum decayed frequency for tm propagating mode we can found this type, but this line is important. If m or n is equals to any of is equals to 0, we will get ez is equals to 0. Nothing matters. In the case of, we will derive now, then we will find the modes of operations according to the lowest order, and find the another component which is not equals to 0. In the case of transverse magnetic in rectangular waveguide, we derive the cutoff frequency equations for different modes, then our calculation becomes over. In the case of transverse electric wave equation, oh, if there is any confusion how this general equation, this type of equation ex ey hx comes, in earlier studies we derive general solution for electromagnetic waveguide, and then after derivation we know this general solution for transverse electric wave and general solution for transverse magnetic wave. We use these basic equations in the case of transverse magnetic, and in the case of in transverse electric, these equations, and mainly we put the values in it, kx, ky, kc's, and then we get our desired results. In the case of transverse electric, it will be kinda same, but we cannot apply the mm, second order derivative equation, cause here ez will be 0 cause it is transverse electric. So we first to go with, after applying the boundary condition, we go with the az, then go with the ex, then go with the ey to put the boundary conditions value and get our kx and ky, like parallel plate equations. In the case of parallel plate, we also saw our previous classes, transverse magnetic waveguides are pretty easier to derive than transverse electric, cause in the case of transverse electric we saw ez, the the working parameter of transverse magnetic becomes 0, so we cannot work with the ez. Then for that we have to derive the second order equation in a different way. In this case, a little difficult, so we familiar with this process, how we can derive this transverse electric wave. Then we putting the boundary conditions again. By putting the boundary conditions here, we can get the value a prime, b prime, c prime, and d prime, the variables which we intuit, and then the putting the value of a prime, b prime, c prime, we derive the equation of kx and ky. We get kx is equals to m pi by a, n pi by b, ky is equals to the pretty similar of transverse magnetic wave. In this case, if I go to the video again, in the main difference between a transverse electric and transverse magnetic, we in the case of transverse magnetic we see that the aim of n, either anyone will be 0, our value of z will be value of, if we see any of this becomes 0, our value z will be 0, and here z also 0 is, because this is transverse electric. But in the case of this is pretty different. Here if m or n is equals to 0, then it the transverse components, some transverse components will be 0, but not, but if any of them gets the value, any gets any value, then it will be not. Here we can see an example. If m is equals to 1 and n is equals to 0, here we can see ex will be 0, but in the case of transverse magnetic we see that dy will also be 0, but here it isn't. So here we can see uh, the m, the value of m of n depends depends on the value of m on m of m and n. We can get different type of transfer components. Here we found ey and hx. If m is equals to 1 and n is equals to 0, and m equals to 0 and n equals to 1, we get here this type of components. The pretty opposite of this one, I guess. Pretty opposite of this one. Thus we find out the modes again by these things. Here written the modes, and by the depending modes we can get the cutoff frequency by the equations. Here say that T transverse electric, the lowest order mode if both TM and TE waves are excited, and it's called a TE10 called dominant mode, cause the dimensions of waveguide A and B are chosen such that cutoff frequencies allow only transverse electric 10 mode to exist in the waveguide. It's the design, default design, I guess. Then here some talk about transverse electric 10 mode, how this works. If we put the value in this case says, then we will derive these equations where transverse electric 10 modes. Here our end of this topic. I hope I am able to understand, teach this topic well. In the case, in the previous sections we will talk about parallel plate. It's pretty similar to the previous one. If you understand the previous one, you will understand this definitely. Just major differences, in the case of parallel plate we deal with two surfaces, and here we deal with the four surfaces. Thank you very much for this listening. Assalamu alaikum.